What is up, multivariate gang? This is the last video in this section, not this chapter. I said chapter in the last video and a few videos ago. We are all still in the same chapter, chapter 11. This is the last video in this section, introducing vectors. We're going to be talking about unit vectors and a process called normalizing vectors. Let's go ahead and get down to it. All right. What is a unit vector? Unit. Unit. Do you know a unit? Anything else? I think you guys do. We've got to get real small here. We've got our unit circle. Yeah, we got our unit circle. And our unit circle has a radius equal to 1. What is a unit vector? Well, we can define a unit vector if we want to do it really fancy. And we can say any vector whose initial, if you had a vector v, whose initial point lied on the origin, its terminal point would lie on the unit circle. That is a way to think about it. It's a way to think about it. It's a cool way to think about it. It's also a dumb way to think about it. If I'm going to be totally frank, a unit vector is any vector whose length is 1. So I'm just going to write that down. Length of v equals 1 if, two f's, meaning if and only if, v is a unit vector. And there is another way to write this case. It's a v with a little hat. That little hat means it's a unit vector. There are 3 pretty famous unit vectors that I haven't talked about with you guys, but you guys definitely need to know them. They are I hat, J hat, and K hat. Okay. So all their lengths are 1, obviously, but what is their direction? I hat goes in the positive x direction, J hat goes in the positive y direction, and K hat goes in the positive z direction. So if you have our x, y, and z axes, here, starting at the origin, you've got our 3 unit vectors, I hat, J hat, and K hat. Now, why are those so important? Well, the reason those are so important is because another popular way to write unit vectors is the way I've been doing it is the little bracket notation. 147, that one. Goes 1 in the x, 4 in the y, 7 in the z. That's the way I like to write them. But the way that you'll see them written a lot is you will see a vector expressed as the sum of scalar multiples of the unit vectors. What do I mean by that? Now, what I mean is if I went, so you have your vector 147. You go 1 here, 4 here, 7 here. Boom. Vector 147. Now, that also means if you went 1, if you add 1 unit vector I plus, then you go over, you add 4 j vectors, then you add 1, 2, 3, 4, 5, 6, 7 k vectors. K plus K plus K plus K plus K plus K, 1, 2, 3, 4, 5, 6 plus K. You get the same vector. Those 2 vectors are the same. going 1 in the x direction, 4 in the y direction, 7 in the z direction is the same as adding 1 I vector, 4 j vectors, and 7 k vectors. So another way you will see this written is as I plus 4j plus 7k. That is actually a weirdly popular way to write them, as the sum of these unit vectors, which I don't understand at all, because I think this is just so much dumber than this. But to each their own, I guess. You guys really need to know, to do basically any of the problems in the book, that those two are equal to the same thing. Okay, so what is a unit vector? Obviously, a unit vector's length is 1, can point in any direction, and you gotta know these guys. Those guys are super important. I hat, j hat, and k hat. Yeah, that's it on unit vectors. Unit vectors have some other properties that make them useful in other situations, and we'll talk about those as we get to them later. Normalizing vectors. All right. So to normalize a vector means just to make it a unit vector. So if you have our vector v over here, we just want a vector whose length is 1, but points in the same direction. And going from v to v hat, that's called normalizing. Well, how do we normalize? Well, the one thing we know about unit vectors is that their length is 1. And the one thing that we know about the length of vectors, well, we probably know more than one thing at this point, but the square root of let's do vx squared plus vy squared plus vz squared is the norm, the length of the norm of the vector v. Now, to get this side to equal 1, we had to divide both sides by vector v. So what does that mean? All right. So if we know that this piece is also equal to the square root vx squared plus vy squared plus vz squared all over the norm of vector v squared, right? Because we just square this so we can put it under the square root. We can split this up, get vx squared over the norm of v squared plus vy squared over the norm v squared plus vz squared over the norm of v squared. All that equals 1. So in order to find the components of this vector v hat, all we gotta do is we gotta take the components of v and divide by the norm of v. Now you're probably going like, what? No, let me finish this off. Vx norm of v squared plus vy norm of v squared plus vz norm of v squared. Now this represents the norm of a vector v hat whose components are vx over the norm of v, vy over the norm of v, and vz over the norm of v. Beautiful. Yeah, so to find this unit vector whose direction is the exact same as this vector, we have to normalize it or divide each component by the norm of vector v. Right there. Boom. All right, example problem. Normalize v if v equals 1, 4, 7. Okay, well, first we got to find the norm of v. And that is, so that's 1 squared plus 4 squared plus 7 squared. 1 plus 16 plus 49, which equals square root of 56, which is equal to 2 times the square root of 14. Yeah, because that'd be 4 times 4, which is 16 plus 40. Yeah, cool. All right. So that's our norm. Then we divide each component by the norm. So v hat equals 1 over 2 square roots of 14. That'd be 4 over 2 square roots of 14, which is just 2 over square root of 14. We get 7 over 2 times square root of 14. Your book is probably, your book nor your homework is probably going to make you simplify those radicals. Okay, that's it for normalizing vectors. You guys have made it to the end of section 2 in chapter 11. Congratulations.